getting derivatives of parametric equations, and that'll prepare you for the textbook problems. And then I'm going to justify the chain rule in real life so that you can gain a more conceptual understanding of the chain rule, so it's not just an algebraic understanding. And that's not going to help you in any way except give you some intuition. And so tonight's homework is the parametric equation stuff, and then to do the first half of the review Xerox. And I've got another review Xerox after this, so by the time you get to that test Tuesday, you'll have done 2 review Xeroxes and an infinity of problems, and hopefully that'll prepare you. But let's go ahead and start with slope of parameterized curves. Here we go. Slopes of parametric equations. Okay. Let's say I gave you this. Let's say I told you x equaled cosine t and y equaled sine t. Okay? And I wanted you to find dy dx. That is, I want you to give me an expression for the slope of that curve at all points. In fact, I'll give a couple of points at t equals 0 and t equal pi over 2. Find the slope of those 2 points. Well, it turns out you can get an expression for the slope of a parametric equation by using the chain rule. The chain rule says this. If I had dy dt, that would equal dy dx times dx dt. Are you okay that that's the chain rule? Essentially, the dx is canceled. And so if I solve for dy dx, I get dy dt over dx dt ends up equaling dy dx. Now, many of you would not have found this by doing chain rule. Many of you would have just said, why don't I just start with dy dx and then divide top and bottom by dt. So I'd get dy dt over dx dt. And the fact of the matter is, that's fine. You can think of it that way if you like. So regardless, if you want the slope of the tangent of parametric equations, you're going to have to get the derivative of the y guy and put it over the derivative of the x guy. And that'll be your expression for the slope of the tangent of a parametric equation. So in this case, y prime is going to be dy dt over dx dt. And my dy dt is the cosine of t. And my dx dt is the negative sine of t, right? And so there we go. That's my expression for y prime. So y prime of 0 is going to be the cosine of 0 over the sine of 0, which is infinity or undefined. And y prime of pi over 2 is going to be the cosine of pi over 2 over the sine of pi over 2, which ends up being 0. In fact, I can even graph this guy. This guy becomes a circle. That is, when t is 0, I get 1, 0. When t is pi over 2, I get 0, 1. So, and so on. So the graph of this guy is just a circle, a unit circle, okay? Where this is t equals 0 and this is t equals pi over 2, etc. So it's a circle that goes in that direction, counterclockwise. And so do you see when t is equal to 0, my tangent line is vertical, so it makes sense that the slope is infinity or undefined. And when t is pi over 2, my tangent line is horizontal, so I get 0. Hey, that's it. Just do dy dt over dx dt. So can I give you guys one for you to do?
Mm-hmm.
Thank you. Go ahead and try this. What if I gave you this, if I told you x was equal to, oops. x was equal to t squared plus t, and y was equal to t to the third minus 5t squared. Let's say that was my relation. I'd like everyone here, first of all, to get me an expression for dy dx, and then go ahead and get me y prime of y. Good luck. Tear. So the Terran's will not come back. Terran's homework is on the desk. Cool. Oh, but Terran didn't have homework come back. I didn't pass back to Terran. Interesting. No Terran homework.
Good job.
Is there anyone who doesn't know what to do right now? Hopefully everyone knew to actually treat this as dy dt over dx dt. So the derivative of the top guy is going to be 3 squared minus 3t squared minus 10t, and the denominator is going to be 2t plus 1. How many people got that? Yay. Okay, then let's go ahead and just stick in a 1. So you stick in a 1, and I got 3 minus 10 over 2 plus 1. So I got negative 7 over 3, negative 7 thirds. How many people got that as the slope? Yay. Okay, hey, that's all there is to getting slope of the tangent. Now, that's not the same as dy dt or dx dt. They have meaning in and of themselves. So what happens is, let's say I were to graph this function here, and I think I'm going to actually do it. I mean, what the heck? Why not? It only takes a minute. Here, just a second. Is this thing going to be in the way?
Now you're good.
Yay. So here we go, mode. I'm going to be in parametric mode, boop. And so I'll go boop. And so what was it? The x was what? T to the...
This is t squared plus t.
Okay, t squared plus t. T squared plus t. And the y was a t to the third minus 5t squared. Okay. And now my window, what should my, I think I'll go with 0 to like 4 or something. Okay. And my step will be 0.1. And so if I'm going 0 to 4, the biggest x is going to be is 20. So I'll go 0 here, 0 to 20. The scale, I'll go in increments of 2. And my y, we see 0 and then 1. It goes negative initially, so like goes negative 5, let's say. And by the time I get to 4, it's 64 minus 80. Oh, so it's really negative. So I'll go like negative 30 to 0, how about? And increments of 5. Boop. So here comes my graph. Alrighty, well that was interesting. So that's the graph, correct? And so, just a second. Oh, stupid thing. Yeah, just a second. I just. There we go. What happened to my graph? Okay, so there's the graph. And so I'm gonna go trace t equal 1, which is whatever I got the slope. And so there's t equal 1. So maybe I'll reduce it to like, let's go x max being 5 and y min being like -10. Okay. Well, anyway, so if I chose that point right there, and I found the slope of the tangent of that point, the slope of the tangent would be -7/3. But what's the meaning of dx dt and dy dt? I mean, those are in my equation, right? I dealt with them with the chain rule. Well, what is their meaning? Okay, so imagine this particle. And this is something that people in physics are going to find a lot more easy to understand than people in calculus. Imagine this particle moving along this curve, and so the particle's moving in this direction, right? I mean, I could actually show you it moving. You know, movie. See how it's moving? So here, let me go backwards. Okay, here we go. I'm moving, look at me. So the point is, someone who has me for physics, what's the meaning of dx dt? What's that telling me?
Distance?
No, not distance.
Oh.
It's a rate of change. What is it the rate of change of? X with respect to time. And what do we call the rate of change of a distance with respect to time?
Velocity.
Like I go 5 miles in 1 hour. What do we call that?
Velocity.
Velocity. So tell me specifically, what velocity is this if it's the rate of change of the x with respect to time?
Horizontal?
Yeah, the horizontal component of velocity. That's showing you how much progress they're making in the horizontal direction. And your y is showing you how much progress you're making per unit time, that is your velocity, in the y direction. Let me ask you this question. dx dt, according to what you're seeing here, is dx dt positive or negative? dx dt, that is your progress in the x direction, the rate of change of the distance, with your x component of velocity. Is it positive or negative?
Positive,
How do you know?
because it's going to the right.
Thank you, Leilani, because it's going to the right. You see, this particle, yeah, I know it's going along this curve, it's going diagonally, but it's moving to the right. Its progress is to the right. You tell me, dy dt, is it positive or negative?
Negative.
It's negative. Why do you know it's negative?
It's going down.
Because it's going down. You see? So I want you to see that dx dt and dy dt have meaning. They are the rate of change of x with respect to t and the rate of change of y with respect to t. So if x was and y were actual distances, it'd be your x component of velocity and your y component of velocity. So yeah, dx dt ends up being 2t plus 1, right? So that dx dt evaluated at, here, let's do it like this. dx dt evaluated at t equal 1 ends up getting you 3. So if this was like meters and seconds, it'd be 3 meters per second. Whereas dy dt is 3t squared minus 10t, and so dy dt evaluated at t equal 1 ends up being -7, you know? So your progress in the x direction is 3 meters per second or feet per second or whatever, and your progress in the y direction is -7. Is there any question or problem in that? Okay, well, you'll get a chance to do problems like this, and then what's going to happen is when we hit chapter 10, we start doing this big time, and we totally investigate these concepts. So now this is more just an introduction than anything. Chapter 10 is when we hit that really, really hard. But I just thought you should know. Alrighty, well, hey, there's not any more for me to say, and algebraically it's actually pretty simple, so I'm pretty confident you guys will be able to get right answers tonight. So,
Is that the chain rule in real life?
what's that?
Was that the chain rule in real life?
No, now that's coming up now. Chain rule in real life. Here it comes. My little made-up lesson of chain rule in real life, because I just felt like when I'm teaching chain rule, it has actual meaning, but I've never really read in a book a good explanation for what the actual meaning of chain rule is, so I decided to just make up my own thing. And we'll see if it helps you or not. I don't know. Here we go. Chain rule in real life. Okay, you're driving a car. You guys okay with that? All right. And so when you drive a car, you are stepping on the accelerator pedal. Okay? So here's your foot. Just like that there. All righty? You guys okay that you've got to step on the accelerator? And so you're going to step a certain distance X. And that's going to make the car go faster. Here, maybe I'll make the pedal have a little bit of width here. So far, so good.
Yeah.
Good. When you step on the accelerator, it makes your car go. So you've got the velocity of the car. The more you step on the accelerator, the faster your car goes. There's a relationship between these two quantities. Well, let's go ahead and define them. We're going to define dv dx. dv dx, it's the change in the velocity of the car due to a change in how far down I press the pedal. Change in velocity of car due to how far down I press the pedal. You guys okay with that? So now I'm going to make up a number. Let's pretend that dv dx ends up being 10 miles per hour per inch. Each inch I depress the accelerator, my car goes 10 miles an hour faster. I'm just making this up. You guys okay with that? Does that make sense? And that's the meaning of these dy dx's and dv dx's. That's what they're actually meaning. They're saying, how much, does this guy change due to a change in this guy? Well, if I depress it 1 inch, I go 10 miles an hour faster. All right? But there's an intermediate step between these two guys, right? Because if I press down on the accelerator, what am I actually doing? Thank you very much. I'm giving more gas to the engine. Okay, so I'm going to define a new variable, a variable called u, and u is going to be gas to the engine. So here's the gas, and I'm going to make some pistons. Just a second. So it looks like an engine. Does that look like pistons and cylinders? So I'm giving gas to the engine, and the gas is being combusted, and that makes the pistons move up and down and turns the crankshaft. Okay, great. And so that means I've got two intermediate steps. I press down on the gas, and I press down on the accelerator, and that impresses, that creates a change in gas to the engine, and then a change in gas to the engine makes my car go faster. Are you guys okay with that? I do this, which creates a change in this, which creates a change in that. And so I'm going to define two new quantities. I've got dv du, which is a change in velocity due to change in gas to the engine. And then I'm going to have du dx. And at this point, I'm going to ask, can someone tell me, what does du dx mean? Yes, Andrew?
Change in gas to the engine due to change of distance between pedal and the floor?
Beautiful. Or really, it's not the distance between the chuck. Yeah, what you said is correct, but I'm thinking more in terms of how far down you press down the pedal. But yeah, same thing. Beautiful. Good. Change in gas to the engine due to press, distance pressing down pedal. How about if I just call it displacement of pedal? Okay, great. In fact, I can say there's a relationship between dv dx, dv du, and du dx. Can someone tell me what's the relationship between these three rates of change? Like, how can I get an equation that relates these three guys, dv dx, dv du, and du dx? I'll give you a hint, it's the chain rule.
D.
Yes, Lauren?
dx equals dv du times dx.
Lauren said dv dx is going to equal dv du times du dx. How many people think that that's correct? They agree with her? Yeah, absolutely. And that's the chain rule. Hey, let's go ahead and assign some numbers to this. How about the change in velocity due to a change in gas to the engine? Let's say that that happened to be 2 miles per hour for every ounce of gas per minute. Okay, so the change is going to be 2 miles an hour for every ounce of gasoline. Alrighty? Are you okay that that's a nice, that's a fine and made up change in velocity due to a change in gas to the engine? I'm going to go 2 miles an hour faster for every extra ounce of gas that goes to the engine. And then the change in gas to the engine due to the displacement of the pedal, well, let's say that happens to be 5 ounces of gas for every 1 inch that I depress the pedal, okay? Well, if I'm gaining 2 miles an hour for every ounce of gas, but I'm gaining 5 ounces of gas for every inch I depress the pedal, how many miles an hour am I gaining for every inch I depress the pedal?
10.
10, right?
Yeah.
Do you see that? Every inch I depress the pedal, I get 5 ounces of gas, and every ounce of gas gets me 2 miles an hour, so I'm going to get 10 miles an hour for every inch. That is, I can write it like this. I get 10 miles per hour per inch because I get 2 miles per hour for every ounce of gas, and I get 5 ounces of gas for every inch I depress the pedal. But it turns out there's another thing that's happening in between, okay? And the thing happening in between is RPM. I want you to see that when I put more gas to the engine, then I get more revolutions per minute of the engine, right? And so I don't need to have just 2 rates of change. I could actually have 3 rates of change. I could say the change of velocity due to a change in depressing the pedal is going to equal the change in velocity due to a change of RPM, right? Multiplied by the change of RPM due to a change in the amount of gasoline I put in the car, multiplied by the change of the gasoline I put in the car due to a change in the amount I depress the pedal. And so on, right? What if there's another intervening? What if I think about like the valves? I don't know, the valves that are letting in and out the gasoline itself, you know? How does the change of the valves affect things? Well, then I'd have a 4th quantity or a 5th or a 6th. And so you can create these rates of change in a never-ending chain. As long as you keep finding relationships inside, you can make that chain longer and longer. And so do you see why they call it the chain rule? Because you can make that thing as long as you want, as long as you keep finding rates of change that relate. Well, anyway, hey, that's my real life example of what's going on here. Okay, so like, let me give you another one. Okay, let's say I make a study of peoples of the world, and I find that the average height of the people of a country depends on how much money the country has. What do you think? The richer a country is, what's going to happen to the average height of the people of the country?
It's gonna increase.
It's going to increase, right? They have better nutrition, better medical care, and so the average height would be bigger. So we've got this quantity, the change of height, how the height is affected due to a change in money. That is, the more money a country has, the more height the people are going to have. But the more money a country has, the more food the people are going to be able to eat, right? So can't I really split this up into a change in height due to a change in the amount of food they eat, multiplied by how much extra food they eat due to the fact that they have more money, right? And if I can find other reasons for why things are happening, I can make that chain bigger and bigger. And so you look around you and you suddenly see the chain rule everywhere, right? I mean, like, let's say grass grows, right? So I've got the rate of change of the inches of grass. And you tell me, what's going to make grass grow more?
Fertilizer.
Okay, well, I'm thinking more water,
Oh.
okay? So inches of grass due to the change in the minutes that the sprinkler is going, right? The more minutes the sprinkler goes, the longer my grass gets. It's magical. But tell me, when the sprinkler goes a long time, what's actually happening? What am I doing?
Drowning your grass.
Yeah, drowning the grass, giving the grass more water, right? So I can say, okay, it's the change of the inches of grass growth due to a change in the gallons of water that the grass gets, okay? And then I got the change of the gallons of water that the grass gets due to the minutes that the sprinkler runs.
Mm.
You see? So whenever you see something changing and you start asking yourself, okay, what's bringing about that change, you find yourself doing chain rule, you know? All right, guys, hey, that was it. I don't know, does anyone have any questions or issues or observations? No? My recommendation is live your life and see how often this comes about. Think in terms of, okay, I've got something changing. What's causing that change? And are there 2 things or 3 things causing the change that I can make into a chain rule? All right, well, that's it. That's the chain rule.